In the previous lecture, we discussed about the carrier transportation mechanism, and in that we discussed the drift of carriers in semiconductor, and we have obtained an expression for current density J, drift current density, that is J is equal to sigma E, and this sigma is the conductivity and E is the electric field, and where sigma is equal to Q into N into mu N plus Q into P into mu P. This is the expression for total conductivity of semiconductor, where mu N and mu P are the mobility of electrons and holes. Mobility means the ease of flow of electron in a semiconductor. So now we are going to see how mobility varies with the temperature and doping. So this concept deals with the collision mechanism or the scattering mechanism occurring in semiconductor. So as the scattering or collision increases, the mobility decreases. So as scattering or collision increases, mobility value will decrease. There are different scattering mechanisms occurring in a semiconductor, that is due to lattice scattering, that is impurity scattering, then carrier scattering. So carrier scattering. So an electron can get scattered. So these are the different type of scattering mechanisms. So depending upon this scattering mechanism, the mobility may vary. So now figure A shows, this is the first figure. So this shows the temperature dependence of mobility with the lattice and impurity scattering. So here at low temperature, so in a semiconductor at low temperature, the impurity atoms will be dominant, and due to this impurity atoms present, there may be impurity scattering occurring in a semiconductor, and at low temperature this will be dominant. This is impurity scattering will be dominant, and the mobility value will be very less. So at lower temperature the mobility value will decrease, and at a higher temperature, as we heat the semiconductor, the lattice scattering will be prominent. Since the lattice atoms vibrate at higher temperature, the lattice scattering will be dominant at a higher temperature. At higher temperature, since the lattice scattering increases, the mobility value will always be low, or it will decrease. So at a low temperature and high temperature, the mobility value is very low due to this impurity scattering and lattice scattering. So we can say at low temperature impurity scattering is dominant, and at high temperature lattice scattering is dominant. At both these temperatures, low and high temperature, the impurity, the scattering value is very high. So the mobility value will decrease at lower and higher temperature. And this mobility due to lattice scattering decreases with the increase in temperature. And at a lower temperature, the ionized impurity scattering decreases with the decrease in temperature. So also this mu I, impurity scattering value, is proportional to T raised to 3 by 2, and this lattice scattering value mu L is proportional to T raised to minus 3 by 2. And the effective mobility due to different scattering mechanisms occurring in a semiconductor can be found out by this expression: 1 by mu is equal to 1 by mu I plus 1 by mu L plus etc. So here we discuss about only impurity scattering and lattice scattering. There are different other scattering mechanisms. So then the effective mobility is determined by 1 by mu is equal to 1 by mu I plus 1 by mu L plus etc. 1 by mu is the impurity scattering that is dominant at low temperatures, and lattice scattering that will be dominant at higher temperature. So next figure B shows the variation of mobility with the total doping concentration. So as doping or as impurity concentration increases, we have already told, as impurity concentration increases, the scattering will increase, so the mobility value will decrease. So this is mobility, mu n or mu p. So as impurity increases or doping increases, the impurity scattering will increase. Impurity scattering increases. So we know that as scattering increases, the mobility value will decrease. So the mobility will decreases as the doping increases. So here the mobility value is decreasing. At a higher doping, the value will be very less. So this is for the silicon semiconductor, and the mobility of electrons and mobility of holes is plotted. Always the mobility of electrons will be greater than the mobility of holes, that we have already discussed in the previous lecture. That is due to the effective mass concept of electrons and moles. And next is since the position of hole is closer to the nucleus than that of electrons, the mobility of electrons is always greater than the mobility of holes. So these are the variation of mobility with the temperature and doping. Next we will see an expression for minimum conductivity. We have studied the total conductivity, so we are going to derive an expression for minimum conductivity. So the total conductivity sigma can be written as sigma is equal to Q into N into mu n plus Q into P into mu p. So this is the conductivity due to electrons, and this is the conductivity due to holes. And for minimum conductivity, the condition is d sigma by dn equal to 0 or d sigma by dp equal to 0. This can be equation 1 for minimum conductivity. This is the condition for minimum conductivity. We have to equate d sigma by dn is equal to 0 or d sigma by dp equal to 0. So I am taking equation 1. Equation 1 can be written as sigma is equal to Q into N into mu n plus Q into, this P can be written in terms of N, that is Ni square by N. N0 P0 is equal to Ni square. So P is Ni square by N into mu P, equation 2. So for minimum conductivity, this d sigma by dn value should be evaluated, and that d sigma by dn should be equal to 0. So d sigma by dn will be Q and mu n constant. So differentiating with respect to n, this will be Q into mu n plus this will be Q Ni square mu p constant. So Q into Ni square mu p constant. 1 by n on differentiation, it will become minus 1 by n square. So this is d sigma by dn. I am equating this value to 0 to obtain the minimum, the condition for minimum conductivity. So on equating, Q into mu n is equal to Q into Ni square mu p into 1 by n square. So this Q cancel, and n square, on arranging, n square will be equal to Ni square into mu p by mu n, and from this we can write n is equal to n square. On taking root, it will become Ni into root of mu p by mu n. So actually this is the condition for minimum conductivity. So there can be two questions. One, it is the expression for minimum conductivity, and this is the condition for minimum conductivity. Condition for minimum conductivity. If we derive the equation by considering d sigma by dp is equal to 0, then we will get a condition in terms of P. So now we can find out the minimum conductivity expression by substituting the value of n equal to ni into root of mu p by n in equation 2. So equation 2 implies sigma is equal to q into n is replaced by ni into root of mu p by mu n. So substituting n equal to ni into root of mu p by mu n into mu n plus q into ni square into mu p divided by n. N is ni into root of mu p by mu n, and this is equal to, and this mu n can be written as root of mu n into root of mu n, and cancelling root mu n, and it will become root of mu p mu n. So the first term will become q into ni into root mu p. This mu n is root mu n into root mu n divided by root mu n. So one root mu n will be cancelled and it will become root mu n. So root mu p into root mu n is root mu p mu n, plus the second term is ni will get cancelled. So q into ni, here one mu p is there, so root mu p into root mu p, and root mu p will be get cancelled, and this root mu n will go to the numerator and it will become similar to the first term, that is root mu p root mu n. So the first and second term are similar terms, and so this can be added and it will be 2q ni into root of mu p mu n. So this is sigma minimum. So the condition for minimum conductivity is substituted in equation 2 and we will obtain the minimum conductivity equation. So this is the expression for minimum conductivity. Sigma minimum is equal to 2q ni into root of mu p mu n. This is the expression for minimum conductivity. So we have to study the total conductivity equation and condition for minimum conductivity, that is n is equal to ni into root of mu p mu n, and also we have to study the minimum conductivity expression, that is 2q ni into root of mu p mu n. Now we will discuss one problem relating to drift mechanism. So here the question is, a silicon bar 0.1 centimeter long and 100 micrometer square in cross-sectional area is doped with 10 raised to 17 centimeter raised to minus 3 phosphorus atom. Find the current at 300 Kelvin. So here a silicon semiconductor is doped with the phosphorus atom. Phosphorus atom means donors. So it is doped with the donors and the value is 10 raised to 17 centimeter raised to minus 3 and the temperature is 300 Kelvin. So we have to, if 10 volt supply is applied, or 10 volt field is applied across the semiconductor, so automatically there will be a drift mechanism and we have to evaluate the drift current, and the data given is the centimeter length, 0.1 centimeter long semiconductor, and the area of cross section is also given and the doping concentration is given. And actually this mu n value will be given in the question paper, and mu n is 700 centimeter square per volt second. At room temperature at 300 Kelvin, the value for mu n with the doping is 700 centimeter square per volt second. For an intrinsic material, the value of mu n is actually 1350 centimeter square per volt second. We know that as the doping concentration increases, the mobility will decrease. So at some increased donor concentration, the value of mu n will be very less than the intrinsic value. So it is 700 centimeter square per volt seconds. So here, so we have to find the current. We know we have the expression for current density, and we have to find the current. So the current means the voltage value is given, so V is given, and we have to find the resistance. So we will get the drift current. So drift current can be determined by V by R. Voltage is 10 volt, and the resistance value we have to evaluate. So R can be found out by rho into L by A. So rho is the resistivity, L is the length of the semiconductor, A is the area of cross section. Again, L is given, A is given, rho is not given. So we have to find out rho. Rho is resistivity. Resistivity means 1 by sigma, or conductivity. We know the value of conductivity. We know the expression for conductivity. Here only mu n is given, and the donor concentration is doped with the donor concentration. So we have to evaluate only the sigma due to electrons. That is the conductivity due to electrons. That is sigma is equal to Qn mu n. Sigma is Qn mu n. Sigma equal to Q into N into mu n. And so by obtaining sigma, we can find out rho. So by obtaining rho, we can evaluate R. If we know the value of R, we can determine the current value. So first find sigma. Sigma is Q into N into mu n. Q is 1.6 into 10 raised to minus 19. N is the donor concentration. Since the semiconductor is doped with donors, phosphorus atom means donor impurities, the majority carrier concentration will be equal to donor concentration. So the N value will be equal to 10 raised to 17 into mu n. Mu n is given as 700. So on doing the calculation, we will get the sigma value as 11.2, and the unit is ohm raised to minus 1, centimeter raised to minus 1. So this is the value of sigma. If we know the value of sigma, we can find out rho. Rho is 1 by sigma. So 1 by 11.2, which will be equal to 0.89. Sorry, this value will be equal to 0.089 ohm centimeter. So rho is 1 by sigma, which is equal to 0.089 ohm centimeter. So we have found out the value of resistivity. Then we can find out the value of R. R is rho. Rho is 0.089 multiplied with L 0.1 by area of cross section is given as 100 micrometer square. So we have to calculate the value in centimeter square. So 100 micrometer square in centimeter square, it will be equal to 10 raised to minus 6 centimeter square. So all the value should be in centimeters. the micrometer square, length, area always should be converted to centimeter. So it is equal to 10 raised to minus 6 centimeter square. So, and this value will be equal to 8.93 into 10 raised to 3 ohm. So the value of resistance of the semiconductor will be equal to 8.93 into 10 raised to 3 ohm. So we can find out the current value. The voltage is given as 10, resistance value is obtained as 8.93 into 10 raised to 3 ohm, and this will be, on solving, it will be equal to 8.93 into 10 raised to 3, sorry, this will be equal to 1 by 8.893, 1 by 8.93 into 10 raised to minus 2, and that value is equal to 1.12 into 10 raised to minus 3 ampere. So this is the value for current. Okay, thank you.